All right, our next one. Now we're going to be taking a polar equation and converting it to rectangular. This one's kind of interesting in that there's not a theta. So let's think about this. Theta is completely unrestricted. In other words, the angle could be anything you want, represents all values, and r is restricted at 2. So if you thought about this graph, what kind of graph would have r equal 2 and theta could be anything? So you might think that could be a circle. Okay, theta could be anything. Basically, all values is going to rotate its way around and create this circle with a radius of 2. So let's see if that works. Now, I have r equal 2, and I know I need x's and y's. So relationship, I have two relationships that tie those together. Tangent involves x, y, and r, because tangent of theta would be y over x. But that's going to introduce a theta, which I don't want to do. I also know that x squared plus y squared equals r squared. This is probably my best bet considering I want to completely eliminate my r's and my thetas. So what I'm going to do is I'm going to do a little trick where I'm going to square both sides to get r squared equals 4. And then I'm going to replace the r squared with x squared plus y squared. So I have a circle where x squared plus y squared equals r squared. So r, or the radius, would be 2, and the center would be 0, 0. So as a little bit of review. But basically what I'm looking for is this rectangular equation. I know there are no r's and thetas left, and I only have x and y's, which makes it rectangular. That's a form I'm used to, so that's a good form to leave it in. Our next example has only theta restricted to 2 pi over 3, which is 120 degrees, but r can be anything. So think about this. I have an angle locked in 120 degrees, so consider this, and then the radius could be anything, positive or negative. Okay, so let's see what actually happens. So this one is literally something that's kind of a trick. Somehow I need to get x's, y's, and theta all in one expression. Tangent is the only thing that involves x, y, and theta all at once. So I am going to take the tangent of both sides, okay? Tangent of theta, therefore, is from our toolbox, or from our triangle, y over x. Okay? If I actually think about unit circle, we have a 60-degree reference angle. And I know that in a 60-degree reference angle, when y is 1, okay, I know that opposite the 60 is square root of 3 over 2. And opposite the 30 is negative 1/2 in this case. So tangent would be a negative radical 3 if I do y over x, or opposite over adjacent. Okay, and remember 2 pi over 3, I just thought of that as 2/3 pi, or 120 degrees, 60-degree reference angle. Now, I see y, x, good news, and some number. The only thing I'm going to do here is I'm going to go ahead and get it all in one level by taking both sides by x, and I would have y equal negative radical 3 times x. That, strangely, is the equation of a line with slope of negative radical 3 over 1, which is this line right there, and a y-intercept of 0. So if you think about our earlier, we have a theta restriction of 2 pi over 3, and the radius could be positive, so anywhere along this side. The radius could be negative, which would be anywhere along this side. Okay, so that would make sense that that would be our equation of our line. Kind of interesting interpretation, but definitely good result. Our next example, polar form, r equals cosecant theta. My goal, remember, is to eliminate r and theta. I don't really think very well in terms of cosecant. Also, none of my tools deal directly with cosecant. They deal with sine and cosine. So the first thing I'm going to do is go ahead and change this to sines and cosines. I know cosecant is 1 over sine. The next thing I'm going to do is to clear out the denominators by multiplying both sides by sine. So I would have r sine of theta equals 1. Since r sine of theta is the same thing as y equal, this is y equal 1. So imagine this. There's our polar equation, r equal cosecant theta. Definitely much more difficult. Our rectangular equation is a horizontal line at y equal 1 with a slope of 0. Much easier to deal with the rectangular in this case than the polar version. Our last example for the day, I included because it has an identity, and always look for those identities. When I see a multiple of theta like I do here, sine of 2 theta, I want to do a replacement. So I know that sine of 2 theta from our previous chapters is 2 sine theta cosine theta. So I'm going to do that substitution. So r would be 5 times 2 sine theta cosine theta. So that means r would be 10 sine theta cosine theta. Now, I need x's, y's, r's as quickly as I can. So what I'm going to do, I'm going to go ahead and take sine and replace it from my triangle as y over r. And similarly, I'm going to replace cosine with x over r. That at least gives me x's, y's, but I still have r. So the next thing I'm going to do, I have an r squared basically in denominator. So I'm going to multiply both sides by r squared to eliminate the denominator, and that would give me r cubed equals 10xy. Now, this one's very unique, and I introduced this one on purpose because it is definitely a challenge. So let's slide this up so I have a little more space. So r cubed is 10xy. I know, and this I would not have expected you necessarily to be able to do on your own, but I want you to see how these things all tie together. I know r squared is x squared plus y squared. I have r cubed. I don't want to introduce an r and think of that as r squared times r because r would be a square root. So instead I'm going to think r squared to what power is r cubed? And if I take r squared, using my properties, to the 3 halves power, I would get r cubed. So I can think of that left side as r squared to the 3 halves power equals 10xy. Now r squared can now be replaced with x squared plus y squared. Whoops. Let's try that again. X squared plus y squared to the 3 halves equals 10 x, y. Now, technically right now, this is an equation that has only x's and y's, no r's and thetas, so it is rectangular. Is that anything we would recognize? Well, that 3 halves power kind of throws things out the window. Okay, we haven't really had anything. It's got an x squared plus a y squared, kind of looks like a circle, but then we have this 3 halves power. So, with that in mind, this is as far as we're going to go. If you're going to look in the back of the book, it might have a variation of this, and if anything, they'd subtract 10xy and set it equal to 0. This one, definitely a challenge. This kind of introduces those top probably 5 to 10% problems that we might run into. That's going to be it for examples for the day. Hope that gives you some good resources for your homework. Thank you.